All right, continuing with number 16, just a suggestion. You might want to just read through the question and see if you can answer it, and then come back to the video and see how you did. That's probably a better approach than just to kind of listen the whole time. See how much of this you can do, and then come back and check to see if there's any revisions you need to make. All right, 16 says use possible symmetry of the graph to determine whether it is the graph of an even function, odd function, or a function that is neither even nor odd. So what do we have to remember about that language, about an even function, odd function? Well, it's about symmetry. So quick review, an even function has y-axis symmetry. Meaning if we were to fold along the y-axis, the graph would create a mirror image of itself. If we were to fold this graph along the y-axis, we don't have a mirror image, so that's not an even function. All right, and last thing to check is an odd function. Well, by definition, an odd function has origin symmetry. So first thing we want to consider is, does the graph pass through the origin? That's a quick, easy inspection. No, this graph does not pass through the origin, so this is not going to be an odd function. Let's say it did pass through the origin. Then the second thing we would check is there a double reflection across both the x and y axis in whatever order you want to do, so that when you do the double reflection, the graph creates a mirror image of itself. So this graph is neither even nor odd. Right, 17 says evaluate the piecewise function at the given values of the independent variable. So here we have presented a piecewise function. So f of x, which can also be thought of as y, is equal to the equation 2x minus 4, as long as the x values that we plug into this equation are less than 0. They're negative numbers. If x is not negative, if x is 0 or greater than 0, then the answer would be found by using the second piece down here, y equals 5x plus 6. So the x is the independent variable, it's the input, and we're looking for the y's at certain x values. So for a, f, evaluate this function evaluated at -3. So these are all x values. So we can't just plug in -3 to both pieces. We have to find the piece where x could be -3. Well, x being -3 means that -3 is a number that's less than 0. So we identify by looking at the restrictions on x, and we see that we want to plug in -3 in for the top equation. And we'll do the work, and we get -10. So f evaluated at this independent variable is -10. Right, when our x value is 0, we're going to have to look at the bottom piece, because this is where x can be greater than 0 or equal to 0. So I'm going to come over here to this equation, and that's where I'm going to put the 0 in. And 4 is our x value. Well, 4 is bigger than 0, so we're going to put 4 into the bottom piece. And just a reminder that this is function notation. That means that these are the ordered pairs, the points that are on the graph of this piecewise function. All right, 18. The domain of the piecewise function over here is all real numbers. And it's just another way to say, let's look at the domain values, the x values. If we were to combine both these sets of x values and put them together, for example, if x is less than 0, if this is 0, if x is less than 0, I'm going to do an open circle, and I'm going to draw an arrow to the left. If I include x is greater than or equal to 0, or equal would fill in that circle, and greater than would go this way. So all real numbers are presented here, so that's why they're saying the domain is all real numbers. We don't do anything with it. It's just that we're presented with a situation where this piecewise function has a domain of all real numbers. And we can verify that by looking at these two sets of x values. Part A, let's graph the function. So we have a piecewise function with two pieces, so that means two t-charts. In the left column of each of the t-charts are our independent variables, which is x here. And in the second column, we're going to put each of the y's, okay, as headers up here. So this is y equals 4x, and this is y equals negative 4x. All right, next thing that we have to be responsible for is figuring out what x values go down here. It has to be purposefully thought of based on the restrictions. So for 4x, this top piece, I slide over here and I go, oh, x has to be less than 0. But let's go ahead and include 0. And over here, we're going to put a little open circle to remind ourselves that when we plot this point, we're going to plot it with an open circle. So x is less than 0, so I'll just generate a few x values less than 0. For the second t-chart, x can be greater than or equal to 0. So you always want to start the two t-charts at the x value of where the break is occurring. But we're going to put a closed circle here to remind us that when we go to plot this point, that we fill that point in because of the or equal here. And then x greater than 0, just generate a few x values. Hopefully these will be enough points to get us an idea of what the graph is so we can connect it and finish drawing it. All right, so let's take turns putting these x values in for this x. And likewise over here. All right, let's build a graph. This is your x-axis, this is your y-axis. So let's come over to this t-chart right here. I've got the ordered pair 0, 0. It's the origin. It's an open circle. And then I'm counting off by 1, so I'll go ahead and put a few tick marks here along the x-axis. So -1. It's good to label one of them so we kind of know what the scaling is. So -1, -4, and I'm going to I want to scale my y-axis, so I'm kind of observing what my y values are here. And they're counting by 4s, so I think I'll do the same thing here. Okay, my scaling along the y-axis doesn't have to be by 1s. It can be a different scaling than what's on the x-axis. All right, I'm ready to plot. So 0, 0, we got the open circle. -1, -4 would be right here. -2 is here, -8's here, -3, -12. So it looks like we've got points that are lying along a line. Let's connect them. And we know we can continue back this way. Just because we only have these x values doesn't mean my graph stops. So we'll indicate that it continues with an arrow. Plotting these points right here in this table, 0, 0. Well, here it is again, but it says let's fill it in. So it happens to fill it in from this second t-chart here. 1, -4, 2, -8, etc. And the points suggest that I could connect, and if I were to add some more x values in that second t-chart, I would just continue probably along that same kind of line there. All right, part A, we graph the function. Now let's use our graph to determine the function's range. All right, so the range. So start from low y's, and let's move ourselves up. The highest y value of a point on this graph would be at y equals 0. So I'm starting at -infinity, and I'm going up to 0, and I want to include the 0 with a bracket. In 19, let's find the difference quotient. That is, this formula will be given to you. Notice that h can't be 0 because we don't want to divide by 0. So let's find the difference quotient for the following function. So you'll be given the formula, and then you'll be given an equation. All right, so in looking at this formula right here, in the numerator, I see that f of x is given to be -4x plus 3. I don't know what f evaluated at x plus h is, and that's my responsibility to find that. So we generate this by coming over here and underneath f of x, let's put in f evaluated at x plus h. That's what we want to find, an expression that represents f evaluated at x plus h. So what we do is we take x plus h and we insert it for this x, substitute it in, and then over here in the equation we put x plus h. And don't forget the plus 3. So we just generated an expression for f evaluated at x plus h. Now we're ready to go to the formula. I have h in the denominator, and I'm going to put -4 quantity x plus h plus 3 up front. And it's a difference quotient, that means subtraction, so I have a subtraction. And I want to subtract f of x, but make sure and put that in parentheses. Let's extend that fraction bar. We're subtracting both these terms, and if we don't put it in parentheses, we're going to forget to distribute that negative to that 3. All right, so we've got some algebra to do here. It's not too bad because we don't have a power to where we have to, FOIL or anything. So let's distribute the -4 in. Arrows are always good. They help remind us, to multiply, distribute into all terms here. Because sometimes students will forget and not put the -4h. They'll just put plus h here. Got the plus 3. I'm here at the subtraction, but remember that acts as a -1 multiplier. So let's draw arrows. That's plus 4x and that's minus 3. All right, we can clean some of this up. I typically start from the back end because everything in the function should cancel with something up front here. So the 3's cancel. The 4x should cancel. It does. If it doesn't, that's kind of like a red flag and you go, oh yeah, I got to go back and see where I might have made a mistake. We're left with -4 times h divided by h. So the h's divide out and our final answer is -4. Kind of a built-in check process. If you have a linear function, not quadratic, the answer to the difference quotient should be the coefficient on the x, that slope value right there. The -4 represents a slope value of this line, this linear function. I think all that content, most of that last content was in section 2.2. These next 3 questions are in section 2.5 if you need something to go back and look at. All right, for these 3 problems, we're going to graph the given function without a calculator. We're going to use, you can have a scientific, but no graphing. We're going to graph them using the parent common functions. There were 7 of them in section 2.5, so I only have 3 here, but I would encourage you to go back and look at the absolute value, the cubed root, and the different ones that aren't presented here. So we're going to graph this function using the common function. Let's do this first. Let's identify the common function. Well, when I study the structure of this equation, I see a square. So the parent function was f of x equals x squared. And hopefully we've kind of had that memorized. It's that parabola that opens up, touching its vertex right here, its minimum at the origin. All right, we've identified the common function. Now let's go back to the equation and go, well, this -3 inside the parentheses with the square on it means we're going to go right 3. Remember, the horizontal shifts are opposite of what we're seeing as far as the operation. So you might think minus is left, but it's horizontally, it's going to be right 3. The plus 4 is outside the parentheses. That's a literal change, so we're going to go up 4. All right, so a real good point to kind of start with and move would be the origin. So let's move this origin point right 3 and up 4. So I'm just going to indicate right 3, up 4. I'll put this vertex right here, and off that vertex, I'm going to draw the correct graph of the parabola. Okay, 21. Let's identify the parent function or the common function. I'm just going to call it f of x. Since I'm already using h here and h here, I don't want to call it h also. The parent function is the square root of x. Let's see if we can remember what that looks like. The square root of x starts at the origin with the endpoint, and it kind of goes up and then over, always increasing. All right, looking at this new equation, I see that the +4 is underneath the square root with the x, so this is going to be a horizontal shift left 4. Draw on my grid. A good point to kind of transform and move and then draw the rest of the graph off of would be the origin point here. So I'm going to take that point, I'm going to move it left 4. So the graph of the square root function now begins here and continues offward. Don't forget your arrows too. All right, for 22, I can kind of look at the equation. I see the exponent of 3. So the parent function is the cube function, f of x equals x cubed. And its graph looks something like this. It kind of swings this way, bends this way, and then when it hits the origin, it kind of concaves back upward like that. So we've got the parent function. I see what the graph looks like. I'm going to look inside the parentheses and say, hey, I've got to move that right 3 and then up 2. Again, the origin's a good point to kind of move and then draw the rest of the graph off of that translated origin point. So right 3, up 2. So right 3, up 2. I've translated the origin to here. Kind of notice that off of that point, you kind of draw the graph to where it bends this way. It's called concave up. And then here, it bends back downward. Now, does it cross over the y-axis? I don't know, but the general shape is what we're looking for here. Again, that was in 2.5. All right, for 23 to 25, on the domain of the function, I want to say that was in section 2.6. When we were finding the domain of the function from equations, not from graphs in section 2.6, we looked at 3 different types of functions. We looked at rational functions, polynomial functions, and even root functions. So I have one of each of them here. This is a rational function. 24 is a polynomial, and 25 is an even root, is the square root. So if you need to go back to those notes and look to see and remind yourself how to find the domain, we're looking for restrictions. Okay, so the language is all back there in those notes. I'm going to tackle 24 first. It's the easiest one. It's a polynomial function. Its domain is all real numbers. There's no fractions, no square roots. It's a well-behaved graph. Let's go back to 23. A rational function, what determines it, the restrictions is the denominator if there's any variables in the denominator. We just kind of discard the numerator. We don't look at it for this question of domain. So what we did is we took the denominator and we set it not equal to 0. We don't want x plus 5 to be a value that gives us 0 because divided by 0 is undefined. So the parentheses aren't necessary. Let's go ahead and subtract a 5. So x cannot be -5. X can be any other number we want it to be, and we won't get 0 if we add 5, but if x is -5, then that gives us the division by 0. And let's put our answers, oh, I should have put up here, put your answer in interval notation. So if this is -5 and we exclude it from our domain, if you need to draw this number line to help you come up with the interval notation, then you know that's a good strategy. So -∞ up to -5, parentheses, union, and then we start again immediately after -5 and go to +∞. Okay, 25. Now, this is not a polynomial. It's not a rational function. It's a square root function. And we never want to find the square root of negative numbers. So the restriction on an even root function is to take this radicand, which is 3x minus 12, and say, okay, I don't want whatever x is right here, I don't want that to be negative. So let's make the expression 3x minus 12 greater than, or it could be 0. Again, parentheses aren't necessary, but just kind of want to show that group there. Let's solve for x now. So as long as the number we plug in for x is 4 or greater, and we do the work underneath here, we will get a positive or zero or a positive answer to take the square root of. So a number line shows this like 4 here, or equal to is closed circle. Numbers greater than 4 go this way. So the domain would be 4 with a bracket to infinity. Any x value number less than 4 when plugged in here would give us a negative number, and then we'd have an imaginary solution. Okay, for 26, I believe this is still content in 2.6. It says first find the sum of the two equations, f and g, the difference, the product. Now remember, this does not equal this notation. Sometimes we think when we see f of g, it means composition. These are combinations, not composition. This is a product. We're multiplying. So we're going to find these, and then we're going to determine the domain for each. So here's f and here's g. So f plus g just means add these two. Just to remind you, because I don't know the notation that's going to be presented, we have two types of notation that mean to do the same thing, to add. We could write it this way, or we could actually apply the x to both f and g. It doesn't matter if you write this or not, just know that these are equivalent. So I'm going to take x minus 3, and I'm going to add 5x plus 8. The parentheses don't matter because I'm not distributing anything other than positive 1 inside, so I really don't need the parentheses. Now let's collect like terms. This will be 6x plus 5. This answer gives us a polynomial, so the domain is all real numbers. All right, let's subtract. Here's the alternate notation, either one of these. All right, so we've got f, and we're going to subtract. Don't forget to put g in parentheses. I don't need the parentheses up front here because that's just a positive 1, so I can remove them, but this negative right here becomes a negative 1 multiplier, so it's minus 5x and then minus 8. Let's put our x terms together, negative 4x. Let's put our constants together, that's minus 11. The domain is all real numbers because, again, we have a polynomial answer. Let's combine by multiplication. So another way to write that is f of x times g of x. Here's f again. We're going to multiply. So when we look at this, this means to FOIL. So 5x squared plus 8x minus 15x minus 24. Collect like terms, that would just be these two. That collects to minus 7x minus 24. That again is a polynomial. It's not a rational function or even root function, so its domain is all real numbers. And finally, let's divide, which alternate notation would look like this, f of x over g of x. Let's put f on top and g on bottom. There's nothing more I can do here other than report its domain, but the domain is not going to be all real numbers because it's a rational function with a variable in the denominator. So let's take 5x plus 8. We don't want that to equal 0. Parentheses aren't necessary, so let's subtract the 8 and divide by 5. Oh, I should put not equal, not equal. So with one restricted x value, my domain is going to exclude that. So we go negative infinity up to negative 8/5, and then start again at negative 8/5. Look at 27. Again, I think this is in 2.6 as well. Yes, these are compositions. This is also in 2.6. All right, for f and g, let's find the following functions. This is not multiplication. This is putting g inside of f. And another way you might see it without that little circle there is that nested parentheses. Actually, I'm going to scoot that over to the left to give myself more room. It gets kind of crowded. So G goes in F, so I put my eyes on F, I look at the equation, and I'm going to put a big parentheses where the X is, because where this parentheses is, this X is where I insert X minus 5. And I'm just going to bring this notation down, just have a good label. So we'll distribute and collect. All right, G of F of X. Let's put F and G. So I go to find G, here's G. G has an X up front, so I'm just going to do a big parenthesis. And G has the minus 5 behind the X. So now I'll put F, or 2x plus 1, inside the parentheses. Parentheses aren't necessary, so I can remove them. And when I collect, I'm going to get 2x minus 4. Right now we're not working with equations, we're working more with we're working with the equations, but we're plugging numbers into the equations. All right, -2 goes in for the X and G first. So when I put that in there, I'm going to get, when I plug -2 into G, I'm going to get -2 minus 5, which is -7. So I'm actually going to swing this down here. So I haven't worked with the F equation yet, but I know that G of -2 is -7. So all of this gets replaced with -7. Now I want to plug -7 into the F equation for X. So 2 times -7 plus 1. So I should put my final answer here. F of G of -2 is equal to -14 plus 1, -13. So basically plug -2 into the G equation for X, get an answer, take that answer and put it into F. I think I'm going to actually work down. I think it works best. So let's first of all find F evaluated at -2. So here's F, plug in -2. Let's see if we can do that mentally. That's -4 plus 1, that's -3. So now let's find G of -3. So let's plug in -3 here for this X and we get -8. So the final answer is -8. And you've probably already noticed that when you reverse the functions, you don't get the same answer. Sometimes you might, it just works out that way. 28 says find F of G of X and G of F of X and determine whether the pair of functions F and G are inverses. As a reminder, inverses are when both these compositions result in an X when we clean it up. So let's find these two compositions, F of G of X and G of F of X. And if both the answers are X, then we know we can say that F and G are inverses. So G and F, here's F. I'm going to insert G. Here I'm multiplying 4, which I can make a fraction by putting 4 over 1 into this other fraction. And these 4's will divide out, leaving X minus 7 on top. And we still have the plus 7. Well, we know these 7's will cancel, so we're just left with X. So we're halfway there. If this composition results in X, then we know that we can state that those two equations, F and G, are inverses. So F goes in G, so here's F, this is G. G's a fraction, here's X up front, we've got the minus 7 in the 4. We're putting F in that slot. The parentheses aren't necessary because we don't have anything in front to multiply, so I can remove them. And when I remove them, the 7's will cancel, leaving 4x divided by 4. And we'll finally divide out a common factor of 4, and we do get x. Yes, these functions are inverses. 29. The function f of x equals x cubed minus 27 is 1 to 1. that means that this function, when graphed, would pass. It passes the horizontal line test. So if a function passes the horizontal line test, like this one doesn't, but if it did pass the horizontal line test, it means that its inverse graph, when you reflect across y equals x, is also a function. Anyway, they're just saying that this function does pass the horizontal line test, so I can find an equation for its inverse. So our objective is find the inverse. This was 2.7. To find the inverse function, we let f of x be y, if it wasn't already. And then inverse functions have the property that we switch the x's and the y's. And then we solve for the new y. So I'm going to have to add the 27 to the other side and take the cube root to get y by itself. I'm going to trade sides as I bring this up here. Okay, I want it y, so I'm going to bring in the cube root. And so we put the cube root over x plus 27. The cube root undoes the third power. We're left with y. We don't need absolute value because it's an odd power. This can't be simplified, so I'm just bringing it down. And they're telling me they want me to use, instead of y, so I don't confuse that with the original y, they want me to use the inverse notation for the function. So I'll just replace this y with this notation. Again, that was in 2.7. Okay, so let's look at the language of the question in 30. 30 says, here's a graph. Does this graph represent a function? It is a function. It passes the horizontal line test. Does this graph represent a function who has an inverse that's also a function? Does the graph represent a function that has that should be an inverse function? Well, if I were to reflect across y equals x, that graph would probably look something like this. That parabola is opening on its side, it would fail the vertical line test. So we know that because this function fails the horizontal line test, it has more than one intersection, this graph fails the horizontal line test. It's not one-to-one, which means that its inverse is not a function. So no, this graph does not pass the horizontal line test. It's not one-to-one. The inverse graph would fail the vertical line test. Well, hope that helped.